Now, again, what can you do? You can define a distribution over the return itself. The return can be negative, right? You can have losses in values, so that's not so much of an issue. There's still a lower boundary. It should not be below minus 100%, right? So if you use the discrete return, the problem persists. So that's another neat application of the logarithmic continuous return that we defined, because the continuous return has a scale that basically goes from minus infinity to plus infinity. So if you use the normal distribution for that, you'll always have kind of sensible prices, positive prices as the result. Right, so theorists like to work with returns as well. And the third argument comes from what we've done in the previous chapter, right? We've worked with, in the present value method, we wanted to know about discount rates. Discount rates are provided as percentage numbers, right? Again, that's the return. So it makes sense to, if we want to learn something about those discount rates, to basically just work with the level of returns. So let's start off with the forward-looking perspective, and I have prepared an example with, I think there are 5 securities in there, and I counted we have 5 rows, so every row is basically getting assigned a different security, and I will let you kind of work through the example together, so you can already take out your calculator, or if you want, you can do this in Excel, it works the same way. Just one comment in Excel there are formulas for both perspectives. So usually they're separated using the P for population and S for sample. So for example, there's a variance formula, which is VAR, and there's the VAR.P and the VAR.S. The sample versions are fine. The population versions are something that you should not use, or basically only in rare instances, because what this function assumes is that the probabilities are the same for all outcomes. So you can use it for a coin flip or dice. But in the example that I show you, we have different probabilities for the different scenarios, so it doesn't work. Right? So be careful when you use the population versions here, because they assume equal probabilities. So it's of course a little bit easier to run down using Excel. Excel doesn't do rounding. However, be aware that in the exam you cannot use Excel, so a little bit of practice with your calculator doesn't hurt. So the first quantity that we look at is sometimes it's called the first moment, and the next will be the second moment. So in statistics, these are called moments of distributions. And the first simple moment is the expected value of a return. The measures that we look at are generally abbreviated with Greek numbers, so the Greek letters. So this one here is mu. Mu stands in for the expected return. And simply speaking, the expected return is just your probability weighted average. It's not a simple average of your returns in different scenarios, but if the return is more likely, it gets a higher weight in this computation. Let me illustrate a little bit my notation here. So we are now in a setting, again, of uncertainty. And I think I have this in the previous slides somewhere, where we have different scenarios, and I usually use trees to illustrate that. The scenarios here will be numbered using the letter I. So the first scenario is 1, so the second is 2, and that the last scenario is capital N for number. Right, so every scenario gets assigned a number. And by the way, I'm using discrete distributions here, where you have a countable number of scenarios. Of course, it works with continuous distributions as well, but instead of taking the sum of the scenarios, you take the integral. So this will be something that it will show up, I think, in the option pricing formula at one point, but don't worry, you don't have to compute integrals here. That's just for problem sets, it's much easier. And it still gives us kind of enough complexity to figure out the most important mechanisms. So we take the sum of the scenarios. So here, that's our scenario in blue. Now for every scenario, we need to know what the return of the security is. Right, so the returns will be R1, R2, and so on, up to R capital N. And we have discussed in the first chapter, if you have share prices, then you would need to have the share price today, and then the share prices in every scenario, and that helps you. And with this information, you can compute the return in every scenario. And finally, we have the probabilities, P, right? So we need to know use the same order as above. So we have P1, P2, and so on, up to P capital. So for all securities that we are going to look at, the first two columns are the same, right? Scenarios and the probabilities are the same. They only differ in terms of the return in every scenario. Again, as we're now using the forward-looking perspective, coming up with the probabilities and those returns in real life is a pretty hard thing. So that's why we have the backward-looking perspective to study that. Right? But most theories, or all theories, are defined using such concepts, using probabilities. So I hope the setting is clear. So then let's have a look at the example. So we have 3 different scenarios. I think I've used blue for the scenarios, and you will find the scenarios in the first 3 columns here, 1, 2, 3. And I've given them names already to make this a little bit more realistic. So this will be our number I for the scenarios, 1, 2, 3. You might see that when I came up with the example, it was pretty recently during lockdown, so there was a vaccine producer in this in the list here. I actually looked at BioNTech, the company, and I have the data for BioNTech in the chapter as well. So to illustrate and show you how you can estimate the values from real data, and BioNTech is the final example in the slides. It's listed in the US stock market, not in Germany, even though it's a German company. So we have the 3 scenarios. I labeled them crisis, and obviously because of the corona pandemic, this would be our lockdown pandemic scenario. This will be kind of a normal scenario, and then I have a kind of boom scenario, which is a good scenario for tech companies, especially here the electric car manufacturer that we have. So this could be maybe Tesla in the real world, right? So you see that has a very high return here, meaning that it's a situation where many people kind of buy electric cars, and this company benefits disproportionately in that scenario. So what else do we see? We have our probabilities. I think I've used red for the probabilities. No, I used green, so use the same color coding. So the probabilities are in the first line. So we have P1, P2, and P3. So it deliberately shows the different probabilities here. And if that's the case, do not use the formulas in Excel for the population. And then finally, we have for our 5 securities here, we have returns. Right, so this will be R1. This will be R2, and we have R3. Right, and these here are basically all returns. So we want to extend the example step by step. Right? So we first start with the expected value, and then we're going to add the other risk measures. Okay, so maybe let's assign. So you don't have to do all of them. So the first row does the supermarket. The second row will do the gasoline car producers. The third row will do the electric car manufacturer. The fourth row will be the vaccine producer, and the row in the back should do the aggregate stock market. And so don't worry about why these are individual stocks and this is the market or a portfolio. You can apply these formulas on single securities or portfolios of securities. It doesn't matter. It makes absolutely no difference. We will talk about the special features of portfolios in the next chapter. Right? So, but here we can just treat it as an individual security. So I hope this one is easy. So I'll give you maybe 3 minutes to figure out. You only have to do one number, right? So depending on where you're sitting here in the room, 5 rows, 5 securities.